Okay, welcome all. In this video, we will discuss stagnation properties. See, in a fluid dynamics, a stagnation point is a point in a flow field where the local velocity will be zero. See, at that condition, if you are going to measure the properties, then the type of the properties are called as stagnation property. It may be a temperature, then it is called as stagnation temperature. If it is a pressure, then it is called as stagnation pressure. Density, then it is called as density stagnation density. See, for example, you can observe the diagram at the section 1 and section 2. See, at the section 1 the properties are velocity, pressure and density. When it is subjected to in a flow, see, it reaches the point or the section 2, and if it is a confined or if it is a closed one, at that time the velocity will become zero. If you are going to measure the velocity, pressure, density, temperature, the section 2 is called as stagnation pressure, stagnation temperature, stagnation density. Okay, in order to describe a single jet of fluid properties with respect to a single jet energy term for internal energy flow work and kinetic energy, let us consider from the figure 1. The figure 1 can be, we already discussed about the figure 1. The figure 1 is explained or understand by certain assumption. The certain assumptions, like here it is flow is steady flow, then the system is open system, then it is insulated. See, then there is no work. If the system is insulated, means there is no heat transfer takes place, then there is no shaft work, then the flow is steady and it is adiabatic. Then we assume here the system is frictionless or the flow is frictionless and reversible adiabatic. Therefore, we know that the steady flow energy equation. We know that the steady flow energy equation, we are going to applying that at the section 1 and section 2. That is m into h1 plus v1 square by 2 plus gz1 plus q is equal to m into h2 plus v2 square by 2 plus gz2 plus w. We know that from the first law of thermodynamics, heat transfer is equal to work. Therefore, that is Q, there is from assumption it is clear, there is no heat transfer and there is no shaft work. Therefore, the Q and W's are 0. Since the pipe is horizontal, Z1 is equal to Z2. Then the remaining terms of the parameters are H1 V1 square by 2, where H1 is the enthalpy, then V1 square by 2 is a kinetic energy and Gz1 is potential energy. Therefore, since it is a horizontal and there is no heat transfer and there is no work transfer, then the equation becomes H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. See, under the constant adiabatic functions, reversible adiabatic conditions, the stagnation enthalpy and kinetic energy remains constant in the absence of shaft work and heat transfer. Then this condition is called as static enthalpy. Sorry, it is a stagnation enthalpy, or it is also known as total head. Therefore, H0 is equal to H plus V1 square or V square by 2, where H0 is called as stagnation enthalpy, H is called as static enthalpy. We know that enthalpy is equal to Cp into T, where Cp is specific heat at constant pressure. We are going to applying that formula. Therefore, from the equation 2, H0 is equal to Cp into T0. T0 is a stagnation temperature. Then H is equal to Cp into 2 plus V square by 2. Cp gets cancels. Therefore, T0 is equal to T plus V square by 2 into Cp, where T0 is a stagnation temperature and T is a static temperature, V square by 2 Cp is a dynamic temperature and V is the velocity of fluid. Therefore, with the help of that stagnation enthalpy, the stagnation temperature properties are derived. Then come to the next property, that is stagnation pressure or total pressure. See, it is defined as a pressure which is measured when a body is at rest condition for a reversible and adiabatic process. Therefore, P0 by P is equal to T0 by T gamma divided by gamma minus 1, where gamma is the adiabatic index, that is 1.4. Then P0 is stagnation pressure and P is static pressure. We will discuss what is the relationship between stagnation temperature, stagnation pressure, stagnation enthalpy in terms of Mach number. See, we know that the stagnation enthalpy, that is H naught is equal to H plus V square by 2. We know that H is equal to Cp by Cp into T, that is the general formula of enthalpy. Therefore, that is applying in the that H naught is equal to Cp into T naught, H is equal to Cp into T, V1 square by V square by 2. You can call it as the equation 1. But we know that from the gas constant R is equal to Cp minus Cv. In that we are going to defining Cp, that is Cp is equal to gamma divided by gamma minus 1 into R. We can call it as the equation 2. Then we need to find V from the equation 1, that is we know that Mach number m is equal to V by C, where C is a square root of kRt, that is a sonic speed or velocity of sound. Therefore V is equal to m into square root of gamma RT. Substituting the value of Cp and V in equation 1, therefore after substitution, after the cancelling of the term, we are going to get T naught divided by T is equal to 1 plus gamma minus 1 divided by 2 m square. See, you can call it as equation 4. This equation 4 shows the stagnation temperature property in terms of Mach number. We can use this formula in order to find out the stagnation temperature by knowing the Mach number. Similarly, for stagnation pressure, P naught by P is equal to T naught by T gamma divided by gamma minus 1. That is nothing but, we know that already T naught by T is equal to, substituting the T naught by T in this equation, then P naught by P is equal to 1 plus gamma minus 1 divided by 2 m square raised to gamma divided by gamma minus 1. See, this equation P naught by P equation is the representation of stagnation pressure in terms of Mach number. See, we'll discuss the note. This is nothing but a formulas. The stagnation enthalpy. Stagnation enthalpy can be determined by H naught is equal to H plus V square by 2, where H naught is a stagnation point, H is the static point, and V is the velocity. Second one is stagnation temperature, that is T naught is equal to T plus V square divided by 2 into Cp, where Cp is a specific heat at constant pressure. The value is 1.005 kilojoules per kg Kelvin, where Cp we need to substitute in terms of joules per kg Kelvin. Next, stagnation pressure. The stagnation pressure is equal to P naught by P is equal to T naught by T raised to gamma divided by gamma minus 1, where some other represent it as gamma as adiabatic index, or some other represent K as a adiabatic index. Both are same, values are same, that is 1.4. Then similarly, these are without considering a Mach number. The same formula with considering the Mach number can be written as stagnation temperature in terms of Mach number, that is T naught by T is equal to 1 plus gamma minus 1 divided by 2 m square, where m is Mach number. Then stagnation pressure in terms of Mach number is P naught by P is equal to 1 plus gamma minus 1 divided by 2 m square whole raised to gamma divided by gamma minus 1. Then last one, stagnation density. The stagnation density can be obtained. The stagnation density rho naught divided by static density rho is equal to T naught by T 1 divided by gamma minus 1, or 1 plus gamma minus 1, substituting the values of T naught by T, that is 1 plus gamma minus 1 divided by 2 m square whole raised to 1 divided by gamma minus 1. Or if you already calculated P naught, that is stagnation pressure, stagnation temperature, you can apply this formula, that is P naught is equal to rho naught R T naught. Therefore, rho naught is equal to P naught, that is stagnation pressure divided by gas constant into stagnation temperature. See, this is the formulas and the concept of stagnation properties.